Hi, in this video, we're going to talk about centripetal force. If you like these videos, please tap the like button. Tapping the like button will help reach a wider audience. And also please subscribe. Thank you for watching. So now we're going to talk about uniform circular motion. Uniform circular motion means moving in a circle at a constant speed. That's what the uniform refers to, constant speed. Now, since the velocity is changing direction, there must be an acceleration. Remember, velocity is a vector, so simply changing the direction of the vector is a change, and a change in velocity is an acceleration. This acceleration points in the direction of the change, which is toward the center of the circle. Now, since the speed is constant, there's no acceleration along the direction of motion, just perpendicular to the direction of motion toward the center of the circle. Now, since we have an acceleration, by Newton's first law, there must be a non-zero force in that direction. And this force we call the centripetal force, and the acceleration is called the centripetal acceleration. The word centripetal means center seeking. All right, now we have to be careful with this because the centripetal force is not a separate force that suddenly appears. It is the resultant of forces that are already in the environment of the object in question. So the centripetal force is not a force in itself. It is the resultant of real forces acting on an object. So for example, the moon is in a nearly circular orbit around the Earth because of the gravitational force of attraction between the moon and the Earth. So it's that force of gravity which supplies the centripetal force, keeping the moon moving in a circle. Centripetal force is not a separate force in itself. It's the force of gravity that keeps the moon in orbit. And since the moon is in a circular orbit, we can call that force of gravity a centripetal force. All right, let's talk about drawing force diagrams for uniform circular motion. So if the particle is in uniform circular motion, both the acceleration vector and the net force vector point toward the center of the circle. Once a particle is set in motion, it wants to move at a constant speed in a straight line. That's from Newton's first law of motion. So if we're moving in a circle, there must be a force toward the center of the circle to push the object into the circle. All right, so that's what's going on in this diagram. The net force vector points toward the center of the circle. That's shown in red. The acceleration vector shown in green. Now be careful, this is the acceleration. Acceleration is not a force. The force supplies that acceleration, so they point in the same direction. Now I've also drawn in the velocity vectors in blue. Now, no matter what path an object travels in, whether it's a straight line path or a curved path or a circular path, the velocity vector is always tangential to the path. So the net force on the particle is the vector sum of forces in the environment. Remember that centripetal force, mv squared over r, is not a force in itself. It is the resultant of forces in the environment. So notice that as this object moves around in a circle, if the force is suddenly gone, then the object will move in a straight line in a line tangent to the circle. So in this diagram that I've drawn, imagine it's a ball tied to a string being swung around in a circle. As the ball gets to the position at the far right, the string suddenly breaks. Now we no longer have a force toward the center of the circle. The ball will want to move in a straight line, and that line will be tangential to the circle. It does not go flying to the outside of the circle. It moves in a straight line tangential to the circle. So there is no force pushing to the outside of the circle. The force is pulling the object into the circle. It wants to go in a straight line, and since it's moving in a circle, the force must either push or pull it into the circle. All right, so here's how we draw a correct free body diagram for an object in circular motion. This is shown at the right in the top figure. The resultant force is toward the center of the circle. The bottom figure shows a common error. Students want to put a force that points away from the center of the circle toward the outside. There is no force toward the outside of the circular path. The real force is toward the center of the circle, so there must be a real force in the environment pushing or pulling the object into the circle. Remember, an object set in motion wants to move in a straight line, so to move in a circle, there must be a force pulling or pushing it into the circle. So why do people think there's a force going to the outside? Well, if you recall the video on friction concepts, I talked about non-inertial reference frames. A non-inertial reference frame is an accelerated reference frame where Newton's laws do not hold. If you are in an accelerated reference frame, fictitious forces appear in those reference frames. But if we step outside the non-inertial reference frame and see what's going on, we see where the real force is. So, for example, if you were riding in a car going around a curve, it feels to you like something wants to push you to the outside of the circle. The reality is the car is forcing your body into the circle. So as the car is pushing you into the circle, so as the car pushes on you toward the circle, it feels like to you there's a force pushing you outside. So that is the fictitious force. There's no such thing as a centrifugal force or centrifugal force. That is the fictitious force that shows up in non-inertial reference frames. If we step outside this non-inertial reference frame, we see that the real force pushes the object into the circle. So be very careful of this. There is no force towards the outside of the circle.
All right, so this is very important. So this is why it's in bold. The centripetal force is not a separate force, but a resultant of forces in the environment of the object in question. Okay, so when we sum the forces to equal ma, as in applying Newton's second law, the centripetal force is the ma. It's not one of the forces that we sum up. It is the result of the sum of the forces. We write centripetal acceleration as v squared over r. And so then the centripetal force is mv squared over r. So we've looked at centripetal acceleration before. Now remember, the time to go once around the circle is called the period, and we use a capital T. And so that's a time. It's measured in seconds. The distance that we go in one revolution is the distance around a circle, which is 2 pi r. So the speed can be written as the distance around the circle, 2 pi r, divided by the time to go around the circle, which is the period t. So the velocity is 2 pi r over t. All right, here's a review question. When a particle moves in a circle at a constant speed, its acceleration is A, constantly increasing, B, constant in direction, C, constant in magnitude, D, constant in magnitude and direction, or E, 0. Now, see if you can answer this before looking at the next slide. Now, if you chose C, it would be correct. It is constant in magnitude. The centripetal acceleration is equal to v squared over r. So if our speed is constant, the magnitude of the centripetal acceleration is constant. It is not constant in direction. Now, it always points toward the center of the circle, but of course it's rotating around the circle, right? So it's not constant in direction. All right, here's another example. You are driving a van around a circular curve of radius r at a constant speed. There is a ball of mass m tied to a string of length L, which is hanging from the ceiling of the van. you notice that the ball swings out away from the curve, causing the string to make an angle theta with the vertical. Given the speed, the length of the string, and the angle, find the radius of the curve. Okay, so this is one of those problems. When you're riding in the van, you are in a non-inertial reference frame. Since you are going around a curve, the van has an acceleration. So you are in an accelerated reference frame, which is a non-inertial reference frame, meaning Newton's laws don't hold. So it appears to you that there is some force pushing the ball to the outside of the circle. The reality is there is no force pushing the ball to the outside of the circle. If we find an inertial reference frame, we step outside the van, we see what's happening. The ball, once set in motion, wants to go in a straight line, but it's moving in a circle. So that means there must be something pulling the ball into the circle, and it's the string that pulls the ball into the circle. So there is a horizontal component of the tension in the string that points toward the center of the circle, which pulls the ball into the circle. Okay, so there is no force pushing out on the ball. This is a common mistake that students make when doing this kind of problem. So let's draw the real forces acting on the ball. Now the ball is moving in a circle with the van, and so we have an acceleration that points toward the center of the circle. This is our centripetal acceleration. All right, so we have the string is the only thing that's tied to the ball. So the tension in the string has a vertical component and the horizontal component. The horizontal component is t sine theta. Notice it's opposite the angle theta. So it's t sine theta, and that points toward the center of the circle. This is the force that pulls the ball into the circle. We have a vertical component, t cosine theta, and that supports the weight of the ball down, the mg. So t cosine theta equals mg, and t sine theta gives the ball the centripetal force. There is no force pushing outward to the right on the ball. That is a common mistake that students make when doing these kinds of problems. Many students want to put a force pushing the ball outward. There is no force pushing the ball outward. The ball wants to go into a straight line, and it's the inward component, the t sine theta, which pulls the ball into the direction of the center of the circle. That supplies the centripetal force. These are the only real forces acting on the ball. All right, so now we have t cosine theta upward equals mg, and we have t sine theta equals ma sub c, or mv squared over r. All right, so from the first equation, t cosine theta equals mg, solve for the tension, and we get the tension equals mg over cosine theta. Then we plug that into the second equation, t sine theta equals mv squared over r. So we replace the t with mg over cosine theta, and then times sine theta, and that equals mv squared over r. Well, sine over cosine equals tangent, and we also have a mass on both sides, so we can divide the mass out, and we end up with g tangent theta equals v squared over r. Now we can solve for r, and we get v squared over g tangent theta. So we were asked to find the radius of the circle, and here we've got it. So if we know the speed of the van, we know the angle theta, then we've got the radius of the circle. Notice it does not depend on the mass of the ball. So it only depends on how fast we're going and the angle. All right, tie a string to a small weight and swing it into a circle above your head. Do you think it is possible to swing it fast enough that the string will become horizontal? So think about this very carefully. Do you really think it's possible to swing it fast enough so that the string becomes horizontal? Well, we're going to answer this question a little bit later. Let's look at another problem first. All right, here is what's called a conical pendulum. So you have a ball hanging from a string, and the ball is moving in a horizontal circle. So there's a tension in the cord that we can break up into a horizontal component and a vertical component. So the free body diagram is to the right. We have an acceleration toward the center of the circle, and it's the horizontal component of the tension in the cord which supplies the centripetal force that keeps the ball moving in a circle. So breaking the tension into horizontal and vertical components, we have T cosine theta upward and the weight of the ball downward, mg. And then we have a horizontal component of the tension, T sine theta, which points toward the center of the circle. And it's the T sine theta that provides the centripetal force that keeps the ball moving in a circle. So this is very much like the one in the previous problem with the ball tied to the ceiling of the van. Okay, so now looking at this free body diagram, and we'll go back to that previous question. Is it possible for this ball to swing fast enough so that the cord becomes horizontal? Well, looking at the free body diagram, for the string to become horizontal, that means theta, the angle theta, will have to go to 90 degrees. Okay. And then what is the sine of 90 degrees and what is the cosine of 90 degrees? Okay. So cosine of 90 degrees, of course, is 0. So that means we will have no upward component to support the weight down. So if theta goes to 90 degrees, we have no vertical component to hold the ball up, right? We must always have a vertical component in the tension of the string to support the weight downward. All right, so looking at the forces in the free body diagram, we see T cosine theta equals the weight mg. T sine theta supplies our centripetal force, mv squared over r. So using the first equation to solve for t, we get t equals mg over cosine. Plugging that into the second equation for the t, we get mg over cosine theta times sine theta equals mv squared over r. Well, sine over cosine, of course, is tangent. So we have mg tangent theta equals mv squared over r. Or mg tangent theta, then we can solve for v squared, and we get v squared equals rg tangent theta. So for the string to become horizontal, that means theta must go to 90 degrees. But tangent of 90 degrees is infinite, which means we will have an infinite velocity. If we have an infinite velocity, then we will also have an infinite tension in the cord. So you can see from the equations here that it is not possible to swing the ball fast enough so that the string becomes horizontal. We must always have a vertical component of the tension in the string to support the weight mg. So we see it is not possible to swing a small weight attached to a string in a horizontal circle. There must always be a vertical component of the tension in the string to support the weight which acts down. All right, here's an example problem. We have a 100-gram coin sits on a horizontally rotating turntable that's shown in the diagram below. The turntable makes exactly 1 revolution each second. The coin is located 10 centimeters from the axis of rotation of the turntable. A. What is the frictional force acting on the coin? And then part B, if the coin slides off the turntable when it is located more than 16 centimeters from the axis of rotation, what is the coefficient of static friction between the coin and the turntable? All right, now again, we're going to apply Newton's second law, so we need to draw a free body diagram. And the best way to do this is now to look at the thing from the edge instead of from the top down. So now the diagram shows looking at the turntable with the coin from the edge view. And the coin is located at a distance r from the axis of rotation of the turntable. So now we're going to draw in the force vectors that are acting on the coin. So note the direction of the acceleration. The coin is moving in a circle, so we have an acceleration toward the center of the circle. So there must be a force acting on the coin, pushing it into the circle to give us that acceleration. So we'll put in the forces and apply Newton's second law. All right, so it's the force of static friction between the coin and the turntable which pushes the coin into the center of the turntable. If we didn't have that friction, once we started the coin moving, it would want to move in a straight line. But since it's going to stay with the turntable and move in a circle, that static friction points toward the center of the circle, which forces the coin to stay in the circle. We also have the weight of the coin down and the normal force from the turntable pushing up. So in the vertical direction, we have the force normal equals the weight. And in the horizontal direction, we just have the static friction, and we can write that as mass times the centripetal acceleration, or mv squared over r. Okay, now to get the velocity, we're given that it makes one revolution every second. And so the velocity then is the distance around the circle, 2 pi r, divided by the time to go once around. So to get the static friction, we need the velocity. So we have mv squared over r equals m over r times v squared. Well, v is then 4 pi squared r squared over t squared, where capital T is the period. So then we have 4 pi squared mr over t squared. Now we have numbers for all those values. We have the mass was given as 100 grams, which is 0.1 kilograms. The radius is 10 centimeters, which is 0.1 meter. And then the period was 1 second. And so we have the 1 second squared in the denominator. When we crunch those numbers, we get 0.395 newtons for this static frictional force. So we got the answer for part A. Now part B says if the coin slides off the turntable when it's located more than 16 centimeters from the axis of rotation, what is the coefficient of static friction between the coin and the turntable? Well, once we get to 16 centimeters, the static friction force is at its maximum value. And we know the maximum value for static friction is mu sub s times the force normal. So it's the coefficient of static friction times force normal is the maximum static friction. And we set that equal to the mv squared over r, which we got from the previous slide. So we have mu sub s mg equals 4 pi squared mr over t squared. Notice the mass divides out, and we get mu sub s equals 4 pi squared r over t squared g. Now we've got numbers for all those things on the right. We plug in the numbers, and we get the coefficient of friction is 0.645. All right, so now we've got the answer to this. So by drawing the free body diagrams, putting in the forces, noting what direction the acceleration is, this turns into a simple problem.
Hi, Dr. C here. I want to ask you to please help support this channel. There are a number of links in the video description to Amazon.com. If you purchase any items from Amazon by entering through these links, even if it's not one of the items listed, I will receive a small commission that helps to produce more content. There is no additional cost to you whatsoever. Also, please leave your comments, questions, or suggestions below. I want to thank you for support of this channel and please subscribe. I hope you find my videos useful.